Hi everybody, got a lot to talk about, so I'm trying to be as quick as I can and still get all the information across. What you're seeing right now is a graph of the function f of x equals 5 to the x power. This is what's known as an exponential function, and the reason is because the variable in this equation is in fact an exponent rather than a regular base number like we're used to. You might have seen graphs like exponential growth curves like this before. This is, for example, how a pandemic gets started. I don't know if you guys have heard of pandemics before, but this is exponential growth behavior, and that's, again, how diseases spread in that exact curve. You'll notice, by the way, not to get political, but for a while it looks like nothing's really happening, and then all of a sudden, holy cow, what just happened? So I just wanted to look at a couple of things on this graph so that we can kind of explore, and this should make sense, this first observation. F of 1, according to f of x equals 5 to the x, f of 1 is equal to 5 to the 1. 5 to the 1 is just 5. So that's why there's a point here at 1, 5. That checks out. F of 2, that's really 5 squared. 5 squared is 5 times 5, that's 25. So that checks out. There's a point here at 2, 25. And of course, f of 3 equals 5 cubed. 5 cubed is 125, and that checks out. So you can see very little. I had to change the scale here so you can see it. It just took a little bit of change in the x's from 0 to 1 to 2 to 3 for my y values to go from 5 to 25 to 125. But what really interested me when I looked at this graph is actually not that, which, I'm used to exponential growth behavior. I've studied it for years. But I look here, and I'm thinking, well, there's a y-intercept right there. What's the y-intercept of 5 to the x? I wanted to explore that a little bit further. So I used Desmos to help me along. And the first thing I noticed was f of 0 equals 1. That apparently means that 5 to the 0 power equals 1, which begs the question, why? Why is 5 to the 0 power equal to 1? If I'm using common sense, I would think it should be 0, or, if there's 0 5s, then that shouldn't be 1 at least. I don't know why it's 1, but this actually makes sense, and we'll see why. Exploring a little bit further, though, I discovered that there's a value here at when x equals negative 1, the y value is 0.2. And I had to remember some of my basics of fractions to realize that 0.2 is actually 2 over 10, or 2 tenths, which reduces to 1/5. And then I noticed that 5 to the negative 1, which is the value of f of x, 5 to the negative 1 power is equal to 1/5. So 5 to the negative 1, 1/5, that's crazy. And then I looked over here, and I also want to know why. Why is that? I mean, I could see that it's true, but why is 5 to the negative 1 equal to 1/5? Why is 5 to the negative 1 not equal to negative 5, for that matter? That's a puppy killer, but we'll talk about that later. Before I do that, f of negative 2. According to Desmos, it says f of negative 2 is equal to 0.04. So I took 0.04 as 4 over 100. There's the 100. 4 over 100 reduces to 1 over 25, and 1 over 25 is 5 squared. So once again, I see that 5 to the negative 2 is equal to 1 over 5 squared. 5 to the negative 1 is equal to 1 over 5, and 5 to the 0 equals 1. That's an interesting observation, and I'm a little curious about that, so I'd like to see what happens, or why that happens. So here is my attempt to get you to see why that happens. I have the function f of x equals 5 to the x. You can see that here, and I have the values, the y values here, according to their exponent rules. Here's my observation. First of all, when we have x equals 1, that's 5 to the 1. When I change x to 2, then I'm multiplying an extra 5. To 3, then I multiply an extra 5. To 4, then I multiply an extra 5. So there's 4 5s when x is 4. There's 3 5s being multiplied when x is 3. What happens if I go backwards? From 4 to 3, I have 1 less 5 multiplied, which means I can divide by 5 to go backwards. In other words, 5 cubed divided by 5 is equal to 5 squared. 5 squared divided by 5 is equal to 5 to the 1. And then 5 to the 1 divided by 5 to the 1 is equal to 1. 5 divided by 5 is 1. And if you keep dividing, you get 1 divided by 5, then you get 1 divided by 5 twice, 1 divided by 5 3 times, and so on. So now you can actually make sense out of negative exponents. The negative exponents are simply telling us to divide by the base this many times instead of multiply by the base this many times. So here are the general principles that we need to go on for this. We have x to the 0 power equals 1. Any number to the 0 power is always going to be 1. That is irrefutable logic. Anything to the 0 power is always 1. Next, we have any number to the -1 power is the same as 1 divided by that number. So if you have a negative exponent, you really should be dividing by the base, not multiplying. If you have x to any negative power, like x to the -5, that would be 1 over x to the 5th power. So you can see the negative m becomes a positive m as the x becomes part of the base or division. Now, there's going to be some exercises I'm going to ask you to do. You're going to use some of your properties of exponents, and then you're also going to be using the definitions of negative exponents and 0 exponents. But before we actually go before I set you on your work, I wanted to share a few things with you. First of all, about how your work should be. But first, I want to clear up a major misconception that students tend to have. Here it is, -2 to the 4th power, and then right beneath that it says -2 to the 4th power. Well, they seem to be asking the same question. Until I go to the calculator and realize that when I type in literally -2 to the 4th power, calculator says -16, where here, in the parentheses, it says +16. Now, I can make sense of the second one because -2 to the 4th is really -2 times -2 times -2 times -2. I can see that as 4. These two multiply to get a positive. These two multiply to get a positive 4. That gives us 16. So what's happening here? What's actually happening is what's called the order of operations. -2 to the 4th power without the parentheses is interpreted by even a Texas Instruments computer and any other computer. It's interpreted as -1 times 2 to the 4th power. The reason for that interpretation is exponents before product. We multiply exponents, or we take care of our exponents before we take care of multiplication. So -1 times 2 to the 4th is really -1 times 4 sets of 2. That's -16, and that's why the calculator gives us that. So that's a very common misconception that students have. Please be careful and watch for your parentheses. That's why I always put parentheses before we put negative numbers to a power. All right. Now, the next thing is, how are we going to ensure that we're actually understanding? And some of you probably hate this about me and my approach to teaching, but in the long run, it's one of those eat your vegetables things. You'll thank me. But a lot of students will memorize the product rule and the quotient rule and all those rules that I told you about in the previous videos. They'll just memorize the rules and try to practice it, and they'll get done with their homework and they'll never think about it again. What I'm trying to do is to get you to appreciate and understand the shortcut that you have. So, the first thing I'd like you to do when you see one of these exercises is to simply apply the shortcut that I just taught in the previous two videos. In this case, it's the product rule. Two numbers of the same base being multiplied together says you should add the exponents. So I add the exponents, and -3 plus 1 is actually -2, so this is 2 to the -2. Now I apply the definition of negative exponents. That's really 1 divided by 2 squared. 1 divided by 2 squared is a quarter. Now, if I didn't have the shortcut, the quotient rule, the product rule, power of a power, power of a product, power of a quotient, and so forth. If I didn't have those rules, then all I would have is the negative exponent rule and the 0 power rule. Then I would have to take 2 to the -3rd, which is really 1 over 2 cubed. 2 to the 1 is really just 2. So 1 over 2 cubed times 2 is really 1/8 times 2, which is 2/8, which is 1/4. So without using any of the properties of exponents except for a negative exponent, I can actually show the same result as if I use my shortcut. Of course, I use a calculator to verify that I'm not doing anything ridiculous. 2 to the -3 times 2 equals 0.25, which, if you didn't know, is equal to 1/4. So, this is the important thing in your work for numbers 13 through 21. You see I have the evens here. You guys are going to do the odds, of course, for arbitrary reasons. But when you do 13 for 21, you're going to need to include 2 methods plus a calculator check. For the other ones, 1 through 11, you're going to calculator check for sure. Any work that does not include a calculator check is not going to be counted. Just to go over this so you understand what I mean by 2 methods again, this is an example of power of a power. We have 3 to the 3rd power to the 2nd power. The power of a power says we're supposed to multiply the exponents. That's 3 to the 3 times 2, which is 3 to the 6th. 3 to the 6 is 27 times 27, or 729. It's fine if you had to use a calculator for that. We're not all savants. So here we have method 2. Method 2 is if I did not have the power of a power rule, what would I do? I would have to take 3 cubed to the second power and write it as 3 cubed times 3 cubed. And then I would have to write 3 cubed as 3 times 3 times 3, and another 3 cubed as 3 times 3 times 3, and that would all multiply together to give me 729. Sorry. And of course, then I'm going to check this with a calculator. The way I check it with a calculator is simply by taking the given expression, not anything I've monkeyed around with. I take the given expression, put it in the calculator as written, and make sure I have the same correct value. So that's the work that I'm going to ask you to do. Again, we're going to do 1 through 21 odds from your PowerSchool learning page. But before I do, I have to do the one last thing, the puppy killers. These are things that I've seen students do in my sordid career, and I would really like to never see them again. For starters, 5 to the negative 3 is not negative 15. That's 2 puppies, 1 shot. Right here we have 5 to the negative 3 is equal to negative 125. That's better, but it's still wrong because we do not get negative numbers when we have negative exponents. You saw the graph at the beginning. The graph at the beginning showed always positive y values, just smaller ones. 5 to the 0 is not equal to 0. By the way, when we're talking about our product rules and so forth, a lot of times people kind of get all boneheaded. They see a product sign, so they see 3 and 3. So they say 5 to the 3 times 5 to the 3 is equal to 5 to the 9. Something else that I see that drives me absolutely crazy is students will do this. They will say 25 to the 6th power. So they're adding the exponents and multiplying the bases. That is the greatest puppy killer of all. That's puppy killer to the power of a 100, and you know how powerful exponents can be. So do not multiply the bases. You add the exponents because you're adding or counting the number of factors, which is explained again in an earlier video, but I digress. Other puppy killers, of course, 5 to the negative 1 oftentimes is called negative 5. That is not true. X to the negative 1 is not negative x. E to the negative 1 is not negative e. You never get negative numbers from negative exponents, so stop doing it now before you ever do. Alright, anyway, thanks for watching. Sorry this might be longer than usual, but that's life. Thanks for watching. Bye.